sometimes on an exam, people, when they want to test your ability to graph something, will give you a function and all of its derivatives, so you don't have to spend your time taking the derivatives. So let's do an example of that. Today is the last day of November. So let's look at the following. Let's say that we were given that f of x is equal to x squared minus 8 over x minus 2 squared. I have to sneeze in a second. And also, we are told that the derivative is equal to 16 minus 4x over x minus 2 cubed. And the second derivative is given by 8x minus 40 over x minus 2 to the fourth. Our job is to graph this in as much detail as possible, including, and so here's the order I would do things in. Intercepts, asymptotes, what I typically call first derivative stuff, meaning the increasing, decreasing sign chart, and any relative extrema. And then the second derivative stuff, which is where it's concave up or concave down, and any inflection points. So that's kind of my list of things I go through when I'm graphing something like this. Now, no, we'll leave that to the end. So let's go ahead and go through the process. We're going to find the intercept. So to find the y-intercept, it's always weird talking to an empty room here. I know you all are there in virtual, but it's a little offsetting. So we're going to set x equal to 0 and solve for y. So y is going to be equal to f of 0, which is 0 squared minus 8 over 0 minus 2 squared, which is negative 8 over positive 4, which is negative 2. To find the x-intercepts, we're going to set the whole thing equal to 0, or y equal to 0. Now, I know I said this every time. When we set y equal to 0, we're setting the whole fraction, or the whole quotient, equal to 0. But that's equivalent to just setting the top equal to 0, because if we set, or if we multiply both sides by the denominator, we get x squared minus 8 equal to 0 times x minus 2 squared is still 0. Solving for x, we get x squared equal to 8. X is equal to plus or minus the square root of 8. For graphical purposes, I do like to simplify this so I know about where it's going to be. The square root of 8 is the square root of 4 times 2. The square root of 4 is 2. So that's 2 root 2. And the square root of 2 is one that you probably will memorize or at least kind of use a lot. Square root of 2 is about 1.4. So this is 2 times about 1.4, which is about 2.8. So just so when we're graphing later, we know, okay, our x-intercepts are almost 3, but not quite 3. Okay, we found the intercepts. Question, yeah. Put the chat up over here. Is it necessary to simplify? So specifically here, this is not necessary. The writing this is approximately 2.8. I'm just doing it because I know later on when I'm going to graph it, that I need to have a good idea of where those points are going to be. So not 100% necessary, but a good idea. Let's find the asymptotes. I usually start off with the vertical asymptote. So vertical asymptote, we're going to set the denominator equal to 0. So we're going to set x minus 2 squared equal to 0. And we're going to get x equal to 2. And that's our vertical asymptote. And then the horizontal asymptotes, we look at the whole function. F of x equal to x squared minus 8 over x minus 2 squared. I would encourage you here to multiply out the denominator. So you get x squared minus 8 over x squared minus 4x plus 4. And since the degree on top and the degree on the bottom are the same, right? There's a 2 there and a 2 there. The horizontal asymptote is going to be y equal to the leading coefficient divided by the leading coefficient, which is 1 divided by 1, which is y equal to 1. All right. That's it as far as the original function goes. Now we're going to find the first derivative stuff. So for the first derivative stuff, we're going to start off by finding the critical values. So critical values, we're going to set our first derivative, which is f prime of x equal to 16 minus 4x over x minus 2 to the third equal to 0 or undefined. To be equal to 0, we're going to set the top equal to 0, just like when we were finding the x-intercepts for the original function. So we're going to set 16 minus 4x equal to 0. We're going to get 4 times 4 minus x equal to 0. So we're going to get x equal to 4. Now let me ask you all, and I want you to type your answers in the chat. What value of x is going to make this undefined? I want to see 3 answers. Just 1 digit. I know you can type it. What can I plug in for x here that's going to make the bottom equal to 0? So one of those is right. It's just 2. So this is undefined if x equals 2. It's equal to 0 if x is equal to 4. And actually 0 itself is not a critical point. If you plug in 0 here, you get 16 on top and you get negative 2 cubed on the bottom, which is just equal to 16 over negative 8. So what I want to remind you all is that even though the first derivative is undefined at 2, and we are going to include it in our sign chart, 2 is not a critical value because it's not in the domain of the original function. So when I do my first derivative sign chart, 2 gets included, so does 4. I look at my first derivative here. I would probably make my life a little bit easier. I would factor the 4 out of the top and write it as 4 times 4 minus x over x minus 2 cubed. When I pick a number larger than 4, like 5, the top is 4 minus 5, which is negative. The bottom is 5 minus 2, which is positive, and a positive number cubed is still positive. So you have a negative divided by positive, which is negative. And then to do this the fast way, we're going to note that both 4 minus x and x minus 2 have odd powers. The 4 came from the 4 minus x, which has an odd power, so the sign is going to change. The 2 came from the x minus 2 cubed, which has an odd power, so the sign is going to change. Or you could test points. You could test x equal to 3. 4 minus 3 is positive. 3 minus 2 is positive, and the positive divided by positive is positive. You could check 0. 4 minus 0 is positive. 0 minus 2 is negative, and the negative number cubed is still negative. So it's in positive divided by negative, which is negative. So that means our function itself, the original f, all right, I should have written f prime over here. Our function f is decreasing, increasing, decreasing. So I have a relative maximum at x equal to 4, because it's increasing and decreasing. I'm going to find the y value as well. And then a relative minimum. Okay, here's what you need to ask yourselves very carefully. Do we have a relative minimum at x equal to 2? Yes or no? Well, it is decreasing and increasing, but we don't have a relative minimum there because the function's undefined there. We have it too, and I actually like to draw this in when I'm doing my sign charts here, is we have a vertical asymptote at 2. So we cannot have a relative minimum at 2. 2 is not a critical value. Okay. For our relative extremum, we should find the x and y coordinates. So if x is 4, y is going to be f of 4. If I plug that back into the original function, which was x squared minus 8 over x minus 2 squared, that's going to be 4 squared minus 8 over 4 minus 2 squared. 16 minus 8 is 8. 4 minus 2 is 2. 2 squared is 4. So we get 2. Cool. That is, so notably here, I'm starting to have a pretty good idea of what the graph's going to look like. It's going to go down, 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 and then up, max out at 4, and then down after that. but I should still find the second derivative stuff before I do all that. So we can probably fit it in here. Now let's go ahead and use another page. We're gonna have another page for the graphing anyway. So for the second derivative stuff, again, we're going to find the critical values. So the critical values are going to be set the second derivative, which was 8x minus 40 over x minus 2 to the fourth equal to 0. I would factor out an 8 from the top. We have 8 times x minus 5 over x minus 2 to the fourth equal to 0 / undefined. So we're definitely going to get x equal to 5. And we're also going to include x equal to 2, but we're all going to remember we know it's not actually a critical value. So making our sign chart for the second derivative, 2 and 5. Pick a number larger than 5, like 10. 10 minus 5 is positive, 10 minus 2 is positive, positive or positive is positive. And then you can do the same thing we did last time. The 5 came from the x minus 5 to the first. Since the power or the multiplicity is odd, the sign is going to change. The 2 came from the x minus 2 to the fourth. Since the power is even, the sign is going to stay the same. Here, concave down, concave up. So it looks like we have an inflection point when the concavity changes at x equal to 5, and y is going to equal f of 5. If I plug 5 back into the original function, that's going to be 5 squared minus 8 over 5 minus 2 squared, which is 25 minus 8 over 3 squared, which is what, 617 over 9? Cool. All right. We have all the pieces that we can have. Now we're going to graph it. That's a pretty straight lines. I'm pretty proud of myself there. All right. So let's see. So we have, let's go back to the beginning. Our intercepts were x is 0 and y is -2. And then y is 0 and x is plus or minus the square root of 8. And remember, the square root of 8 is about 2.8. So our x-intercepts are maybe like there and there. There's someone joining us. Let's see who's, just curious who's joining us here. We have Rocco, Betty, Anna, and Astasana. Welcome, Astasana. It's a purely everyone's virtual today kind of deal. So I'm talking to an empty classroom here, which is a little strange, but fine. Just make sure you all ask the questions you want to ask so that I can answer them. We're currently working on graphing the function x squared minus 8 over x minus 2 squared. We found we were given the first derivative and the second derivative. We found the intercepts. We found the x-intercept to be, sorry, the y-intercept to be -2. The x-intercepts to be plus or minus root 8, which is about plus or minus 2.8. We were just about to graph them. So there's my x-intercept that's positive root 8. There's an x-intercept that's negative root 8. And then we had a vertical asymptote at x equal to positive 2. So vertical asymptote at x equal to 2. And we had a horizontal asymptote at y equal to 1. And then we had some critical values. We had the critical value x equals 4 was a relative maximum and had a y value of 2. So I plot the point 1, 2, 3, 4, comma 2. There's my relative maximum. So when I draw a relative maximum or something I know is relative maximum, I kind of like to draw this to remind myself, oh yeah, it's going up towards it and then down after it. And then I have a inflection point at 5, 17 over 9. Now I don't know exactly what 17 over 9 is, but I know it's a little bit smaller than 2 because it's less than 18 over 9. And it should be smaller than 2 because 2 right here, right, that's the y value of this relative maximum. So it's kind of the highest point in its vicinity. So over here at 5, it's going to be just slightly lower. All right, so let's see if we can graph. So this, and now when I graph it, here's what I do. When I graph it, I look back at my sign chart for my first derivative. I'm like, okay, my first derivative, let's do this. Let's see if I'll make it a little bit nicer here. You can kind of see both things here. Maybe you can kind of see both things. Yeah, okay. So from the left all the way up until I get to 2, it's decreasing. So decreasing. Oops, I kind of came with this too hard. Decreasing, 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 decreasing. Like that. After 2, from 2 to 4, it's increasing. 2 to 4. And then from 4 onward, it's going to be decreasing again. But I have a horizontal asymptote, so I'm going to be decreasing, but I'm going to kind of flatten out like that. Concave down, and right here we change from concave down to concave up. And again, a couple ways of thinking about concavity is it's opening downwards, opening downwards, opening upwards. Or you can also think of it being concave down, because if it's concave down, any tangent line should be above the graph. If it's concave up, any tangent line should be below the graph. So yeah, it definitely has the right concavity there. I don't usually think too much about the concavity when I graph things. I kind of adjust it afterwards. Okay, questions about any of what we've done for this problem before we do another one? I'm gonna bring enough water with me. It's not gonna be good. It's having a real day here. Yeah, there was more water in that bottle. Okay. All right. So I don't see any questions. So we will move on to another example. Yeah, let's do a similar-ish example. Make sure it's in order here. I'm always happy to go back if you have questions. And you are welcome to unmute yourself if you want to say words, but you're also welcome to type things in the chat if you want to type things in the chat. Let's do a similar kind of deal with, let's look at this. Let's say we've got the following function. G of x is equal to x squared over x minus 3. And we'll do the derivatives ourselves because they're not too terrible here. So let's start off, we're going to graph it. So graph it, meaning find all the things. So always start off with the intercepts. So intercepts. For the y-intercept, you're going to set x equal to 0, and you're going to get y equal to 0 over 0 minus 3, which is 0 over negative 3, which is 0. Cool. X-intercept. Set the whole thing equal to 0. But really, you're just setting the top equal to 0, which is also going to give you x equal to 0. Asymptotes. Vertical asymptote, set the denominator equal to 0. You get x minus 3 equal to 0. So you get x equal to 3. And finally, for the horizontal asymptote, we don't have one. And the reason we don't have one is because the degree on top is greater than the degree on the bottom. But we do have a slant asymptote, also called an oblique, because the degree on top is exactly 1 larger than the degree on the bottom. So to find the slant asymptote, since the degree on top is 2 and the degree on the bottom is 1 less than that, which is 1, we're going to use polynomial division. So x minus 3 into x squared plus 0x plus 0. So x times x would give me x squared. X times x is x squared. X times negative 3 is minus 3x. We subtract. X squared minus x squared is 0. 0x minus 3x is positive 3x. Bring down the 0. Now, I'm going to stop at the right moment here. What do you multiply by x to get 3x? You multiply by 3. And right there, I should stop. I don't need to do any more work. Y equal to x plus 3 is my slant asymptote. Great. We found all the original function stuff. Now we're going to find all the first derivative stuff. So here we are going to find the first derivative. So let's give ourselves some room here. So f prime of x, so it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the denominator squared. Let's simplify. So here we do really have to simplify, because if we're trying to find critical points, we need to be able to write the numerator and denominator kind of as simply as possible, or as factored as possible. The denominator already is factored. The numerator, if we distribute here, we're going to get, let's see, 2x squared minus 6x minus x squared all over x minus 3 squared. 2x squared minus x squared is x squared minus 6x all over x minus 3 squared. And then I would factor out an x from the top and write it as x times x minus 6 all over x minus 3 squared. So now we can find our critical points or critical values. Our critical values are going to be, setting this equal to 0, you get x equal to 0 and x equal to 6. Seeing where it's undefined, you get x equal to 3, but again, I will remind you all every time, not a true critical value, because it's where we have a vertical asymptote. As soon as you see something's a vertical asymptote, you'd be like, oh yeah, that one's never going to be anything else. You can't amount to anything else if you're a vertical asymptote. You're stuck. You're just a vertical asymptote. You have no aspirations or hopes and dreams of being anything other than a vertical asymptote. Specifically, you can't be a relative max or a relative min or an inflection point, because there's no points defined on the vertical asymptote. Sign chart for the first derivative. So we're going to put 0 and 3 and 6. 0, 3, 6. Okay, and then one of the reasons we factor the first derivative as completely as possible is to make it easy as possible to figure out the signs of things. So pick a number larger than 6, like 20, positive, positive, positive. So the whole thing is positive. If you pick something between 3 and 6, like 4, positive, negative, positive. So the whole thing's negative. Or you could say the 6 came from the x minus 6 to the first. The power is odd, so the sign changes. That's a good idea. You know, I hadn't thought about doing it that way, but I love that suggestion. Yeah, you could. I've been drawing the vertical asymptote in like that, but it is also, I love that. A good idea to say, oh yeah, it's undefined there. We cannot have a relative max or relative min. That's a primo suggestion. Thank you very much. I will start doing that probably. That's a good idea. I like that a lot. Okay. Over here on the other side, so when we cross from one side of 3 to the other side of 3, the 3 came from a factor that has an even power, so the sign is going to stay the same. Or you could plug in 1. Plugging in 1, you get positive, negative, and even though this inside part's negative, a negative number squared is still positive. So it's really a positive times a negative divided by a positive, which is still going to be negative overall. Finally, 0 came from the x to the first factor that has an odd power, so the sign is going to change. So our function is increasing, decreasing, decreasing, increasing. So what do we have at 0? A relative maximum or a relative minimum? Give me a thumbs up for a maximum, a thumbs down for a minimum. There's actually there's a thumbs up or thumbs down button I think you can use. Maybe. Maybe not. Wow. I'm not seeing any thumbs. Just disappointing, but okay. Well, it's increasing, decreasing, so we know we have, oh, there's a thumb. Yeah, okay, great. You found, maybe it was hard to find. Cool. Yes, and those are thumbs up. We definitely have a relative maximum at x equal to 0, comma. We already know that when x is 0, y is 0, because that is our intercept. And then over at 6, well, since it's not increasing, decreasing, it's decreasing, increasing, we would have a relative minimum at x equal to 6. And the y coordinate would be 6 squared over 6 minus 3. So 36 over 3, which is 12. Which means I'm probably not going to be drawing this super to scale. Point of interest here, just I think it's worth mentioning. Normally, when you're graphing things, you're not asked to write the intervals where it's increasing or decreasing. But I want to point out that here, this function is increasing on the interval from negative infinity to 0, union 6 to infinity. And it's decreasing on the interval from 0 to 3, union 3 to 6. We cannot just say it's increasing from 0 to 6 because it's not defined at 3. Whereas if it was defined at 3, we would say it was decreasing from 0 to 6. So just a point of clarification there. All right, let's go ahead and find the second derivative stuff. Oh, we have to find the second derivative to find the second derivative stuff. So using our first derivative in the unfactored form, f prime of x is x squared minus 6x over x minus 3 squared. So the second derivative is going to be, let's go up here. F double prime of x is, let's see, so it's the bottom times the derivative of the top, which is 2x minus 6, in parentheses, minus the top, times the derivative of the bottom, which is 2 times x minus 3 to the first times 1, all over the denominator squared. So it's x minus 3 squared, which is x minus 3 to the fourth. All right, we have to simplify. And there's a key thing here. When you take like a second derivative of a quotient, the first time you took the derivative, oh, sorry, I started calling my function f when I started with g. Oh, well. Sometimes we'll just call it f because I wrote f every other time. When you start taking the derivative of this, the first time you get the denominator squared, and then the next time you get the denominator squared again. But here's what's going to happen. I'm going to be able to simplify this so that I end up with an x minus 3 to the third, because I should be able to factor out an x minus 3 from the top. So let's see. I definitely have x minus 3 there and an x minus 3 there. So I'm going to factor out an x minus 3. So I'm going to get x minus 3 times, let's see. So here I'm left with x minus 3 to the first times 2x minus 6. Over here I'm left with the minus x squared minus 6x times a 2 times an x minus 3. Oh, no, sorry. I factored that x minus 3 out. There's none of those left. Sorry about that. It's garbage. All divided by x minus 3 to the fourth. But now I can cancel one of those with one of those. Let's keep them simplifying. I've got, let's see here. So multiplying this out, I have an x times 2x. I have an x times negative 6. I have a negative 3 times 2x. And I have a negative 3 times negative 6. Distributing the minus 1 times the 2, so a minus 2 to each of these terms. I have a minus 2x squared. And a minus 2 times negative 6x is a plus 12x. Divided by x minus 3 to the third. Okay, simplifying. This one kind of always feels a little bad when you simplify it. 2x squared cancels with negative 2x squared. Negative 6x plus negative 6x is negative 12x. Plus 12x cancels out. And so we're left with 18 over x minus 3 cubed. And my only point of interest on my number line is going to be x equal to 3. And I was going to try and trick you guys and make you point out that you don't have an inflection point at 3, but I'm just going to follow Barry's advice and be like, well, I know the function's undefined at 3, so let's draw an open circle there. So now if I look at the second derivative, pick a number larger than 3, like 4, 18 over a positive number is positive. If pick a number smaller than 3, like 2, 18 over negative 1 cubed is 18 over a negative number, which is negative. So my function is concave down and then concave up. And we know we don't have an inflection point where we change because it's undefined though. All right, let's try graphing this thing. So let's see, I've got 0, 0 as my only intercept. I have asymptotes. Let's see, I have a vertical asymptote at x equals 3. I don't have a horizontal asymptote, but I do have a slant asymptote at y equals x plus 3. So to graph that, I would normally graph y equals x plus 3 by finding the y-intercept, which is 3, and the x-intercept, which is negative 3. And then drawing the line through them, but drawing it as a dashed line. That's an asymptote. Cool. And then our critical points are relative extrema. We have a relative maximum at 0, 0. So I know it's a maximum there. So it's going to be like that. and I have a relative minimum at 6, 12. Okay, so this is going to be kind of off the charts here. Sorry. 4, 5, 6. We pretend like that's 6, 12, even though it's probably not very accurate. So that's a relative minimum. And then using my first derivative sign chart to help me graph things here. Like, okay, well, my function should be increasing until there, decreasing afterwards, then decreasing, and then increasing afterwards. And then I should be getting closer and closer to my asymptotes as well. Should be doing something like this. Maybe this wasn't a good idea here. It feels like it's not been working out so great for me when I've done this. Oh, wow. And then like that. And then my graph is going to be a little bit in the way here. It's going to come down like that. And then off, and away towards my slant asymptote. So that's what this graph looks like. Concave down over here, concave up over here. I will pause for questions while I look at another graph. If there's any requests, I'm also happy to take requests as far as graphs go. I have plenty of graphs, but if you have one you want to see. So here's what we'll do next. So I will point out a lot of graphs people like to make you graph are ones that are quotients like that, or I should say rational functions, because they usually have a vertical asymptote and horizontal asymptote or slant asymptote and relative extrema and inflection points and all that. So they kind of have all the features we are looking to test you on, but not every graph has to look like that. So let's look at something like f of x equal to x times the square root of, I'm going to change this one just a little bit. Hopefully it won't be too terrible. Let's say 16 minus x squared. And actually, there's something we've kind of been ignoring for all these graphs, which we should be more careful about here. Before I did any of the things I did for either of those graphs, I really should have talked about the domain. Here, the domain is definitely restricted. The insides of that square root have to be greater than or equal to 0. I prefer to factor this when I'm solving this, but really you can kind of see that x has to be smaller than 4 and not smaller than -4, because if x was like -5, this would be negative. If x was +5, this would be negative. But I can factor it. I could factor it as 4 minus x times 4 plus x. And then looking at the number lines for the domain here, if x is 4, -4, pick a number larger than 4, like 5. 4 minus 5 is negative, 4 plus 5 is positive, and the negative times positive is negative. And then we change signs, and we change signs, and then I want it to be positive or 0. So my domain here is just everything from -4 to 4. Kind of weird. Ooh, yeah. Well, so this problem is going to be interesting, I think. All right, let's do the usual thing. So we're going to find all the intercepts. So y-intercept, set x equal to 0. You're going to get y equal to f of 0, which is 0 times the square root of 16 minus 0. But 0 times anything is just 0. X-intercepts, set the whole thing equal to 0. When you have a product equal to 0, we solve it by setting each factor equal to 0. So you're either going to get x equal to 0 or the square root of 16 minus x squared equal to 0. But for a square root to equal 0, the insides have to equal 0. So we really have 16 minus x squared equal to 0. And although we did just factor it up here, I mean, we could factor it again and get x equal to 4 and x equal to -4. We could also solve this by saying 16 equals x squared, and then the square root of 16, I should say x equals plus or minus the square root of 16, which is 4. So there's my 3 x-intercepts, 4, 0, and -4. All right, the first derivative stuff is going to be a little bit weird here. So first derivative stuff. we're gonna have to use the product rule to take the first derivative. So f prime of x is gonna be 1 times all that. I should say the derivative of x times that, 16 minus x squared, plus x times the derivative of that. Oh, I should really think of this as 16 minus x squared to the 1/2 power. So the derivative of that's going to be 1/2 times 16 minus x squared to the negative 1/2 power times the derivative of the insides, which is 0 minus 2x. And now we really have to simplify this. So let's do a little bit of simplifying here. The 2 and the 2 can cancel there. And I can rewrite this as, I'm going to write 16 minus x squared as 16 minus x, sorry. I'm going to write 16 minus x squared square root of as 16 minus x squared to the 1/2. 1/2 times 2 cancels out, but if you have a minus sign, so I have a minus x squared times 16 minus x squared to the negative 1/2. And then just like in the previous problem where we were finding the second derivative and simplifying it, we're going to do the same sort of thing here. We're going to simplify this by factoring out the smaller power of our common factor. So I'm going to factor out a 16 minus x squared to the negative 1/2. Here I'm left with 16 minus x squared to the positive 1. Because if you multiply that by that, you add the powers, and negative 1/2 plus 1 is positive 1/2. Minus x squared times all that has been factored out. So times 1 if you like. Simplifying this, we end up getting 16 minus x squared is 16 minus 2x squared. Divided by 16 minus x squared to the positive 1/2 power. Okay, so let's set this equal to 0 / undefined. So what's going to make it 0? Well, 16 minus 2x squared has to equal 0. 16 equals 2x squared. 16 divided by 2 equals x squared. Again, we're getting plus or minus the square root of 8. How interesting. It's purely coincidental, which we know is approximately plus or minus 2.8. Great. And then if we want to make this undefined, it's going to be where the denominator is 0. So 16 minus x squared equals 0, which is just x equal to plus or minus 4. And those are technically actually critical values here because they are in the domain of the original function. So drawing our number line, well, so I'm going to draw the number line, but I should actually do it. So I was going to do this, but really what I should do is I should say my ends are negative 4 and 4, and you can't go beyond that. So our critical values are negative 4, 4, and then we had the square root of 8 and the negative square root of 8. Yeesh. So luckily there's a nice number between the square root of 8 and 4. It's the square root of 9, which is 3. If I plug in 3, 3 squared is 9, 2 times 9 is 18, 16 minus 18 is negative. On the bottom, 3 squared is 9, 16 minus 9 is positive, so you have a negative divided by a positive. Between negative root 8 and root 8, I would plug in 0. The top is positive 16, the bottom is 16 minus 0 to the 1/2, which is also positive. Positive, positive. And then finally over here, if I plug in negative 3, I'm going to get negative again because negative 3 squared is still 9. Negative 2 times 9 is still negative 18. 16 plus negative 18 is still negative, and the bottom is still positive. That's our derivative. So our function is decreasing, increasing, decreasing. And now here's where we have a little bit of weirdness. I definitely know I have a relative minimum at negative root 8. So relative minimum at x equals negative root 8. And I guess if I want, I really, we'll find the y values in a minute. Relative maximum at x equal to positive root 8. And as far as I'm concerned, that's the end of the story as far as relative extremely goes. But I know that for at least in some of the web work questions I've been seeing for the other class, we would actually count negative 4 as a relative maximum as well, because technically the function is just getting smaller after it, so it is bigger than everything that it is next to. And in a similar way, and we'll see this graphically when we graph it, we would count 4 as a relative minimum because it is smaller than everything that is next to it, because the function is small, getting smaller, 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 and ending right there. Again, we'll see it more when we graph it, but I just wanted to point it out. If I plug in now, we'll wait to find the y values when we have more room. The second derivative stuff is always gnarly here. So let's find the second derivative stuff. There's our first derivative. Now let's find the second derivative using the quotient rule. So f double prime of x is going to be the bottom 60 minus x squared to the 1/2 times the derivative of the top, which is negative 4x, minus the top, which is, I didn't really miss up enough room here. 16 minus 2x squared times the derivative of the bottom, which is going to be 1/2 times 16 minus x squared to the negative 1/2 divided by the derivative of the inside, which is a negative 2x. Sorry, did I say divided by? I should say multiply by the derivative of the inside, which is negative 2x. And then all that divided by the denominator squared. And yes, we have to simplify this as much as possible. So just like last time, we're going to factor out, I see a 16 minus x squared to the 1/2. I see a 16 minus x squared to the negative 1/2. I'm factoring out the smaller power. So I'm going to factor out a 16 minus x squared to the negative 1/2. And I also see that there's an x, there's actually a negative 2x here, and let's just say there's an x I can factor out from each of these. Let's make it the negative x though. I can factor out a negative x from each of those as well. So here I'm left with a 16 minus x squared to the positive 1 and a negative 4. Oh, sorry, a positive 4. I just want to point out, right? If I multiply this by all of that, that times that, you add the powers, you get 16 minus x squared to the 1/2. Negative x times 4 gives me my negative 4x. Check. Minus, okay, we got 16 minus 2x squared. The 1/2 we'll write down in a second, but the 16 minus x squared to the negative 1/2 completely factored out to right there. So we're left with the 1/2 times a 2, which is just 1. And the negative x got factored out. So we're not going to write it down. And then I would check that as well. If I multiply this by all of this, I'm going to get 16 minus 2x squared times 1/2 times negative 2x is your negative x times 16 minus x squared to the negative 1/2 is that part right there. So we're looking all right. All divided by 16 minus x squared to the 1. Okay, we're almost there. Bring this down. You're going to get in the denominator 16 minus x squared to the 1 plus 1/2, which is 3/2. Okay, again, I'm going to say the thing I said before. When you do these second derivatives where the first derivative was a quotient and the next derivative is also a quotient, your next derivative always just ends up having a 1 higher power in the denominator after you simplify it. That was true here, right? 3/2 is bigger than 1/2, is 1 bigger than 1/2, and it was true in the previous problem. In the previous two problems, actually, right? The derivative, right? It was x minus 2 squared, and then the derivative was x minus 2 to the 3rd, and the derivative after simplifying was x minus 2 to the 4th in the bottom. And the same thing for this other one. Your original function, you started off with an x minus 3 to the 1st in the denominator, and then we took the derivative, you ended up with an x minus 3 squared in the denominator, and then when you took the derivative of that, even though you had an x minus 3 to the 4th, after you simplified, you end up with an x minus 3 to the 3rd. That is not a coincidence. It always happens that way. If you simplify it correctly, your new derivative, the power in the denominator will always be exactly 1 larger than the power was in the previous function. Whew. Okay, so simplifying the top here, I got a negative x, and inside here I have 4 times 16 minus 4 times x squared minus, distribute the minus sign, minus 16 plus 2x squared. That's why we give you these derivatives a lot of times, because they're just gnarly to figure out. I would have given you these ones if I'd had them written down, but I didn't, so we had to find them. So simplifying this, we have negative x times, let's see, 64 minus 16 is 48. Negative 4x squared plus 2x squared is negative 2x squared. Let's go ahead and factor out a 2 from negative 2 from let's make it a negative 2. Why not? From the insides. So we get a negative 2 times negative x is positive 2x. And factoring in the negative 2 from here, we have a negative 24 plus x squared. All right, we're almost there. So our critical values are going to be, well, that's going to give us x equal to 0. This is going to give us x squared equal to 24, x equal to plus or minus the square root of 24. And then that's going to give us x equal to plus or minus 4 again. Okay, now, something I've said here is not necessarily wrong, but it's not really right. One of these three things is a problem. Remember, we're going from negative 4 to 4. There's 0. And the problem is that the square root of 24 is almost as big as 5. It's over here, off the domain of the original function. This is not a critical value because it's not even in the domain of the original function at all. And unlike the ones where you just have a vertical asymptote, we don't care what's happening on either side of it because the function really just doesn't exist out to the right or out to the left. So if our only critical value is 0 and then plus or minus 4 are the endpoints, then plugging back into or looking at the sign chart for my second derivative here, picking a number larger than 0, like 1, the top is a positive times a negative over a positive, so it's going to be negative there. Picking a number like negative 1, it's a negative times a negative divided by a positive, which is positive. Concave up, concave down. So you do have an inflection point at x equal to 0, y equal to 0. All right, it's a lot. It's a lot. So now let's sum it all up. We're gonna go make the graph as best we can. So let's give ourselves a bit of room here. So we know that our x-intercepts were, I believe they were negative 4 and 4 and 0. Yes, negative 4 and 4 and 0. All right. And then we had some, let's see, intercepts, yep. You know what I failed to do, which I should have at least mentioned? I didn't talk about asymptotes at all because I knew there weren't any. So looking at this function here, right, we know there's no vertical asymptotes because there's no way we can be dividing by 0. And we know there's no horizontal asymptotes because to get a horizontal asymptote, you have to kind of be going either out to infinity or negative infinity. But since the domain limits us to being just between negative 4 and 4, you can't go all the way out to infinity or negative infinity. So it's not, an issue. First derivative stuff. Okay, now is where we have to go back and find the y values I said we were going to find. So my critical values were negative root 8 and root 8. So for x equal to the square root of 8, reminding ourselves that our function is x times the square root of 16 minus x squared. If I plug in the square root of 8 for x there, f of the square root of 8 is going to be the square root of 8 times the square root of 16 minus the square root of 8 squared. Square root of 8 squared is 8. 16 minus 8 is 8. So you have the square root of 8 times the square root of 8, which is 8. And for negative root 8, you're going to get the same thing, except it's going to be negative because you have a negative out in front, but this right here will still be positive. So it'll be negative root 8 times root 8, which will be negative 8. Okay, I might have made this too big. Oh, well. So, yeah, so at root 8, which is about 2.8, our y value is like 8. So that's about right there. And at negative root 8, our y value is about negative 8, which we'll say is about right there. Reminding ourselves of the sign chart for the first derivative. Our function was decreasing, then increasing, then decreasing. So it's going to be decreasing until I get to this point here. Increasing. And then I get my maximum, and then I'm decreasing after that. And be careful with this graph, right? You're not going to extend this to have more arrows, right? It stops. That is the whole graph. And then we can see we have an inflection point right there. And there was, oh, and then I wanted to point out the thing I was saying. So totally, right? We can definitely see that is a relative or local minimum. And that is a relative or local maximum. But some people, not me, but some people, some textbooks like to also say that that is a relative minimum because it is smaller than all the things next to it. And similarly, that's right. And similarly, that is a relative maximum because it is larger than all the things next to it. My personal opinion is that for to be a relative maximum or minimum, the function has to be defined on either side of that point, but not every textbook and or person does it that way. So I just want to warn you. But I think in the other class, the Temer Galiyava class, I think her WebWork questions do have you find this point as a relative minimum or this point as a relative maximum. This one's a relative minimum. So just be aware. All right. Sure. What else? We can do more. I mean, I can do more graphing. Sure, let's do one more. We'll do one more graphing problem. Are there any requests, or should I just pick something? Or we can do something else if you want. Sure, we'll do that one. All right. A selection has been made. Let us look at this function, which I don't think we've looked at before. It's possible we have. I don't really think we have, but we'll take a look at it here. So let's look at f of x equal to 1/5 x to the 5/3 minus x to the 2/3. I will point out this function is defined everywhere. So the domain is all real numbers because you can always take the cube root of any number that is positive or negative. It's just not always nice. So y-intercept f of 0 is going to be 1/5 times 0 to a power minus 0 to a power is just 0 minus 0, which is 0. X-intercept's a little bit more work. We're going to take our function, set it equal to 0. I'm going to factor out an x to the 2/3. I'm left with a 1/5 times x to the 1 minus a 1. And if there's questions about this, you should ask them. I'm actually going to do one more factoring here. I'm going to factor out a 1/5 as well. I'm going to rewrite this as 1/5 times x to the 2/3 times, I divided out a 1/5 there, so it's gone. And 1 divided by 1/5 is like 1 times 5. So I have a minus 5 now. And that's still the same, right? If I distribute the 1/5 back in, I get a 1/5 times x minus a 1/5 times 5, which is a minus 1. That just makes it easier for me to see what the intercepts are going to be. So setting this equal to 0, I either get x equal to 5 or I get x equal to 0. So those are my two x-intercepts. All right. Asymptotes. Are we going to get any vertical asymptotes? No. Because again, we have something that doesn't have any fraction. If you don't have a rational function or something where you have a denominator, with one exception that we haven't covered in this class, you can't have a vertical asymptote. So vertical asymptotes only occur when you have denominators that equal 0, or, which you'll learn about in 16b, logarithmic functions also have vertical asymptotes. Okay. Horizontal asymptote, I feel like is a question that's hard to answer here. Yeah. Here's what I'd point out. If you look at your factored form, if you take the limit of this as x goes to infinity, the limit is x goes to infinity of f of x, meaning what's happening to the function is you go way out to the right. Well, x is going to infinity, so x to the 2/3 is getting really, really big, and x minus 5 is getting really, really big. And a really big number times a really big number is a really big number. Similarly, if we look at the limit as x goes to negative infinity of the same function, That's a negative infinity. You just can't tell that I didn't write the minus sign there. Then you have a really big number to the 2/3, a really big negative number to the 2/3 power. Okay, to the 2/3 power means you're squaring it first, making it positive. So you have a positive infinity. And then the cube root of a positive number is still positive. So you have a positive infinity times negative infinity minus 5 is still negative infinity. And a positive times a negative is a negative infinity. So to the right, we're going to go way, way up. To the left, we're going to go way, way down. But we don't have any horizontal asymptotes because we're not getting close to a specific real number. So also no horizontal asymptotes. Oftentimes you can kind of ignore taking these limits and just kind of see what the first derivative sign chart tells you. But we'll come back to that. So first derivative. It's going to equal, I don't know why I underlined it there. 1/5 times the derivative of x to the 5/3 is 5/3 x to the 2/3. The derivative of x to the 2/3 is 2/3 x to the negative 1/3. We should simplify this. It's going to be 1/5 times 5/3 is 1/3. And 2/3 times x to the negative 1/3. All right, I can factor this, and I need to factor this. I need to simplify this so I can solve it equal to 0. So if each of these have a 1/3 as a coefficient, so I'm gonna factor out a 1/3. There's something else too. So I'm gonna be left with a 1 as my coefficient for the first part and a -2 times my coefficient for the second part. So I factor out a 1/3. 1/3 times 1 is 1/3. 1/3 times -2 is -2/3. But then also I'm going to factor out the smaller power of x, which is x to the negative 1/3. And that should have been outside of my parentheses. Killing myself here. Sorry about that. Let's try that again. I factored out a 1/3. I'm leaving myself room for the x I'm about to factor out. And then I have a 1 times whatever and a -2 times whatever. Okay. So now, as I was trying to say, I'm going to factor out the smaller power of x, which is x to the negative 1/3. When I do that, from the first right here, I'm left with an x to the 1. Again, because 2/3 minus negative 1/3 is 3/3, which is 1. Or if you multiply these back together, negative 1/3 plus 1 is positive 2/3. And then similarly, well, not similarly, if I factor out x to the negative 1/3 here, I don't have anything left. So I just have a times 1. So rewriting this in maybe a more normal way, I get 1/3 x to the negative 1/3 times 1x minus 2. And I would actually really prefer to write this as x minus 2 over 3 times x to the positive 1/3. If I set this equal to 0, the only value I get by setting this equal to 0 is going to be x equal to 2. I'm going to write this up here. If I set x minus 2 over 3 times x to the 1/3 equal to 0, we get x equal to 2 as a critical value. And if we see where it's undefined, that's where we get x equal to 0. Because plugging in 0 here makes the first derivative undefined. I will stress 0 is in the domain of the original function, right? We said the domain had everything. So 0 is a tried and true actual critical value, not one of those ones we were talking about before where it was actually a vertical asymptote. So x equals 0 and x equal 2 are both critical values. Let's look at the sign chart. So here's our derivative. I'm going to write it again. F prime of x is x minus 2 over 3 times x to the 1/3. And our sign chart for this is going to have a 2 and a 0. Pick a number larger than 2, like 3. Top is positive, bottom is positive. Pick something between 0 and 2, like 1. Top is negative, bottom is still positive. Pick something less than 0, like -1. Top is negative, and the bottom is negative because a -1 to the 1/3 power is still a negative number. So we have increasing, decreasing, increasing. So we have a relative maximum at x equal to, what is it? Is it at 0 or is it at 2? Anybody?
0.
It is at 0. And then we have a relative minimum at x equal to 2. For the usual reasons, right? Increasing, decreasing means you have a relative max. Decreasing to increasing means you have a relative minimum. All right, now we're going to find the second derivative stuff. So again, usual deal. We're going to take the quotient rule here. So it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom is going to be 3 times 1/3, which is 1 times x to the negative 2/3. All divided by the denominator squared. Simplifying, I'm going to factor out x to the negative 2/3 from the top. So always, I'm factoring out that smaller power if I can. It's going to be x to the negative 2/3 times, here I'm left with a 3x to the first minus an x minus 2 times 1, because I factored the x to the negative 2/3 out. Over, I would actually multiply this out as 9 times x to the 2/3. Simplifying more, bringing that power down to the bottom, it becomes x to the positive 2/3, and x to the 2/3 times x to the 2/3 is x to the 4/3. And hey, check it out. The thing I've been saying happens every time, happened this time as well. When I take the derivative of something where the power on the bottom was x to the 1/3, after some simplifying, the new power on the bottom is exactly 1 larger. 1/3 plus 1 is 1/3 plus 3/3, which is 4/3. Okay, on top, I've got a 3x minus x plus 2, which becomes 2x plus 2 over 9x to the 4/3, which becomes 2 times x plus 1 over 9x to the 4/3. So our critical values here are x equal to -1 and x equal to 0. -1 makes it 0, and 0 makes it undefined. Number line for the second derivative, again, number larger than 0, like 1. Plug it in, top is positive, bottom is positive, is positive. I'll point out here the bottom is always positive. Any number to the 4th power is positive, and then the cube root of a positive is still positive. So something between 0 and -1, like -1/2, the top is positive still, because -1/2 plus 1 is positive, and the bottom is always positive, so still positive. And finally, on the other side of -1, like -3, the top is going to be negative, and the bottom is still going to be positive, so negative overall. So we are concave down, concave up, so that we have an inflection point at x equal to -1. And plugging that back into the original function, the y value would be f of -1, which would be 1/5 times -1 to the 5/3 minus -1 to the 2/3. -1 to the 5th power is still -1. The cube root of -1 is still -1. So you get a -1/5 minus -1 squared is +1, and then the cube root of +1 is +1. So -1/5 minus 1 is -6/5. Whew. Okay. Now I think we have everything we need to graph it. Let's go ahead and do our best. So again, putting all of the things we found on our graph. We have a y-intercept of 0, 0. We have an x-intercept at 0 and at 5. We have no vertical asymptotes, nor horizontal asymptotes. We had critical points at 0 and 2, and we saw that we had, we forgot to find the y value for 2. So it's going to be kind of gnarly, but we'll talk about this. So our function f of x was 1/5 x to the 5/3 minus x to the 2/3. And actually, I'm going to factor it out like I did when I found the x-intercept. I'm going to write this as 1/5 times x to the 2/3 times x minus 5. So we have a relative maximum at 0, which we already know is that point right there. And so it's going to be a relative max like that. And then when x is 2, we have a relative minimum. If I plug in 2, f of 2 is going to be 1/5 times 2 to the 2/3 times 2 minus 5. And that's kind of gross. 2 minus 5 is -3, so that's -3/5 times 2 to the 2/3 is the cube root of 4. I have no idea what that's equal to. I know it's between 1 and 2. So this is a little bit bigger than 1. It's a little bit smaller than 1. Maybe they multiply together and are close to 1. I don't really honestly actually know. It's okay. So I'm just gonna graph it down here. There's my relative minimum. Oh, but it's up to be at 2, sorry, down here. So we're gonna have something like this. And then I had an inflection point, but I'll graph the inflection point later on. Oh yeah, this one's super funky. So I did myself a disservice here. I drew this way because that's what I often think about when you have a relative maximum. But I don't get that here, and here's why. My relative maximum is at 0, and x equals 0 is where the derivative was undefined. When the derivative is undefined, it usually means the graph isn't nice and smooth at that place of non-differentiability. It usually means you have a cusp or a pointy point, as I like to call it. So really, my graph is not great here. What I actually should have done is I should have said, well, I have my 0, 0. I have my 1, 2, 3, 4, 5 intercept. I have my y, gosh, words, my relative minimum at x equal to 2, and I'm thinking it's about down there, but I don't actually really know. I'm just kind of guesstimating. And then the only other thing that's happening is I know the concavity switches. So looking back at my work here, right, the concavity is concave up between -1 and 0, and between 0 and forever. So it's kind of like concave up here, right? Concave up, here's my relative minimum, 2 comma whatever my terrible y value is, -3/5 comma or times the cube root of 4. And then it's also concave up here, but then at -1 comma -6/5, that's going to change. So it's concave up and then concave down, which is kind of hard to get right the first time you've done it. So concave down, right? Any tangent line is above the graph. Concave up, any tangent line is below the graph. That one's a little bit funky. This one I feel like we did really kind of need to know that as you go out to infinity, the graph goes to infinity. As you go out towards negative infinity, the graph goes towards negative infinity. All right, I think that is all for today. Yeah, it's definitely 10:20, so I should stop talking. Thank you for coming. I appreciate it. And thank you for asking questions and being interactive. We will have class. So next week is the last week of classes. I don't know what we're doing after graphing or if there's anything to do after graphing, but if there is something new to cover after graphing, we will talk about it. If there's not, then we'll just kind of review. We'll definitely have practice finals to look at, and you should come with questions. I'll see you all next week, either in person or on the web. All right, take it easy. Hope you guys have a great day.